Well, hello, Calc 3. This is Mr. Vranek. It is during the coronavirus 2020 quarantine. So, if you were watching this in the future, this is why I made these videos. We have to finish up the year, and we did not get to finish yet. So, for the students that are currently in my class, welcome. I hope to see you guys on Zoom or some other conference thing. We're going to split this up into a bunch of mini videos and maybe an assignment or two. You can get everything on Canvas. This is the first video. This is our last section of the chapter we were working in about Green's theorem. Before we actually talk about Green's theorem, there's going to be two ideas that we're going to talk about. The first one is called divergence. So we did talk about flux on, I think, 2 sections ago when we were talking about work and circulation and vector fields. So what divergence is, it's the flux density of a vector field. So what that means is how a vector field is moving at a point. The way to calculate it is if you are given a field where you have an I and j component at a point, then to get the divergence, all you have to do is take the I component with respect to x and the j component with respect to y and add them together, and that gives you the divergence. One extra point that I forgot to write down. If it's expanding, your divergence will be positive. So what I would say also, if you're taking notes down, you could always pause the video and write. That's the nice thing about videos, so I can keep going and not wait for you guys to write. So pause if you need to keep writing, otherwise I will go down to the next section where we are just calculating a quick divergence. Again, this is going to be helpful to change the flux equation into a double integral later using Green's theorem. So find the divergence of this field. Well, again, this field, this is the m and n or I and j components. So if we just use the formula that I just gave you up above, we take the derivative of m with respect to x, and we get 2x, plus we take n with respect to y, and that is x minus 2y. And since we have like terms, we can combine like terms, and we get that the divergence of this field is 3x minus 2y at any point xy. That's how easy it is to calculate a divergence. So again, today we're going to start slow. We're going to learn about divergence and the k component of curl, and then we're going to stop. And that's all I'm going to teach you today. Tomorrow we'll get into Green's theorem. So again, this will be used to find or to change our flux integral into a double integral, as opposed to a line integral or yeah. So the next thing we have to talk about is also how to convert our work or our circulation integral that we learned from 7.2. And to do that, we need to know what the k component of the curl is. So what it does is this lets us know how the fluid is circulating. So I'm going to just scroll up here so you guys can pause it if you want to and look at it. There's some nice little diagrams on the side here to show you. Counterclockwise circulation will be the positive, and then it's showing how the vertical axis is the k component. So as this is spinning, this k component will let us know how the fluid is circulating. It's a value. It's called circulation density, and it is a scalar. So to calculate this, we did curl before, and we're actually going to do it again with Stokes' theorem. The curl is actually the gradient crossed with the field, and so you get a bunch of different partial derivatives, but we only want the k component of that. And so when you only get the k component of curl, when you're dealing with 2 dimensions, it's the derivative of the second, or the j component of the field with respect to x, minus the derivative of the I component of the field with respect to y. And that is what the k component of curl is. Okay, again, this will be very important because this will let us know how to convert our work integrals that we had in 7.2 into double integrals for circulation. Okay, so the last thing we're going to do today, because again I want to keep it nice and short. Oh, by the way, if you need to pause, you can pause here, and we're write some more stuff down. Okay. Oh, don't look at Green's theorem yet. We'll do that tomorrow. I mean, you can actually write it down if you want. I'll put it up here. We'll do this. So let's just find the k component of the curl of this vector. It's the same vector. So this is my m component or I component, and n, which is with the j component. And then to find the curl, remember we need to find the first component with respect to y. And that is -1. And to get the other piece, it's the second component with respect to x, which is just y. And then the k component of curl, or the curl dotted with k, is equal to dn dx, so this one first, which is y, minus dm dy, which is -1. So the k component of curl is y plus 1, or the circulation density, if you want to call it. Okay, so that is as simple as it is to find the k component of curl and also the divergence that we did earlier. Again, divergence will be used with the flux equation. K component of curl will be used with the circulation equation for Green's theorem. And so finally, if you want to write this down today, you can. So what Green's theorem will let us do? It'll let us change our flux and circulation line integrals into double integrals for easier calculation. Fields do not need to be conservative. I don't know if you guys remember that we tested for conservative fields and we were able to find potential functions with that. That's very useful when fields are conservative. This is useful for any type of flux or circulation line integrals. Now I will say that sometimes it actually doesn't make sense to use Green's theorem. Sometimes, especially if it's circular, because you can easily parameterize a circle with one path, and then because of that, sometimes it's easier just to do the original integral for that. Where this really comes into play is if we have paths that are linear in nature, such as squares, rectangles, triangles, because if we had to do the way we did it in 7.2 with parameterizing each path, we would have to do basically 3 or 4 separate line integrals based on the parameterizations of each path going around that square or going around that triangle. Whereas this lets us change it into a double integral, which we learned about earlier this semester, and it'll make it easier to calculate. Okay, so that is the first lesson. Again, very simple. Divergence and the k component of curl. Otherwise, known as the flux density of a vector field or the circulation density. I will see you guys later.